Secondly, today we're just going to make extra sure that we're clear on the words that we use to describe waves. So imagine that I have sent a transverse wave along a piece of string and I've then photographed it. We're going to want to talk about how far a point on the string has moved from the middle, and so we call that the displacement of a point on the wave. So for example, I might say this point here, what's its displacement at right now, the time I took the photograph, what was its displacement? And its displacement, let's say it was, I don't know, 8 centimeters. Okay, and so the displacement of this one looks to be about 16 centimeters. Okay, and this one here, that one, notice that's the maximum displacement that a point on the wave can have. And so that one is called amplitude. Amplitude is the maximum displacement. Now the wavelength, as I'm sure you know, is the distance from one peak to the next, and it's got this symbol lambda. Sorry, I've just said one peak to the next, but that's actually one trough to the next. Here's one peak to the next peak. So you can choose any point on the wave and go a whole wave later, and the distance between those 2 points is the wavelength. And finally then, we've got 3 quantities which we can't find on my photograph. To find those, we're going to need a displacement time graph instead. And what this shows is the displacement of just one point on the wave. So let's say that we had chosen this point here, and we've just looked at this, we've just measured where this one was, and we've plotted its displacement time graph. Okay, notice we can still get the amplitude, the maximum displacement for the point from this graph, and we can still find its displacement at any particular time t. But what we can also now get is the time it takes the point to get from maximum displacement in one direction all the way to maximum in the other direction and all the way back again. In other words, we can get the time it takes the point to go through one complete cycle, one complete oscillation, and that is called the time period of the wave. Now notice, if you were stood at this particular point on the wave, it would also be the time it takes for one complete wave to go past. So we can calculate the frequency, which is how many waves go past per second. Let's say that it takes half a second for a wave to go past. That means that 2 waves are going to go past per second. And I just want to point out here that in base units, that means that frequency has the units per second, second to the -1. This is the number 1, it doesn't have any units, but this is a divide, and so it's per second. Of course, the standard units for frequency are hertz. So 1 hertz is 1 wave per second, or 1 s to the -1. And one last word for this video, the wave speed, so the speed that the wave is travelling. And we have a formula for that. It's the frequency times the wavelength. We measure the frequency of a wave by plugging the thing making the wave or the thing receiving the wave into an oscilloscope, and then the oscilloscope trace will have the same frequency as the wave has. Okay, so pause the video and have a little go at this question now. Okay, so you always get told how much time one square represents in the horizontal direction, and we're going to use that to get the time period and then calculate the frequency. But don't just go from one peak to the next peak. Do as many waves as you can and then average, as this increases the accuracy of your value. Okay, so I've got 1, 2, 3 complete waves there with 9 squares, and each square is 0.50 milliseconds. So that means that 3t is equal to that. Three time periods is equal to 9 of squares, and then we get the time period is 0.50 milliseconds, which to 3 sig fig comes out as 667 Hertz.